The subject of this talk is a comparison of the blowout behavior of turbulent premixed ammonia, hydrogen, nitrogen air flames with methane air flames. The experimental work was done at the Norwegian University of Science and Technology by me, Sam Wiseman, with James Dawson and also Andrea Gruber from SINTEF. The numerical work was done at Sandia National Laboratories by Martin Rieth and Jacqueline Chen, and also with input and coordination by Andrea Gruber. There are three parts to this presentation. First, I'll talk briefly about the motivation for studying ammonia, hydrogen, nitrogen blends. Then I'll describe some blowout experiments. The results of these experiments motivated DNS conducted at Sandia National Laboratories. Those DNS results will be presented in the last part of the talk. Ammonia is a synthetic fuel, sometimes described as a hydrogen carrier. It is easy to store in large quantities as a liquid, and can be burned as a liquid at engine pressures, or as a gas with minimal heating. However, the flammability range and the flame speed of premixed ammonia air flames are significantly worse than many other fuels. Partial dissociation of ammonia, which gives a mixture of ammonia with hydrogen and nitrogen in a 3:1 molar ratio, is a very effective way to improve the combustion properties. Blends can be selected to match many of the laminar flame properties of well-studied single-component fuels, such as methane, propane, and ethylene. The figures show the adiabatic flame temperature, the unstretched laminar flame speed, and the thermal flame thickness of a blend with 40% ammonia, 45% hydrogen, and 15% nitrogen on a molar basis. Methane is shown by the black lines for comparison, and there is a close match in the laminar flame properties over a wide range of lean equivalence ratios. These properties were calculated from 1D flame simulations. Aside from the practical interest in ammonia blends, they provide an opportunity to extend a variety of combustion models and empirical correlations to multi-component, non-equidiffusive reactant mixtures. In this study, we focused on lean blowout limits. On the left is a cross-section of the experimental rig used for the blowout experiment. It's an axisymmetric rig. The flames are fully premixed and unconfined, so they are open to the ambient air. These flames stabilize in the recirculation zone behind the bluff body. The reactant velocity, or blowout velocity, that I refer to in this presentation is the bulk velocity through the annular injector port, defined by the volume flow rate of reactants divided by the projected area of the port. The procedure we used to determine the blowout limits was to ignite a stable flame and then slowly increase the airflow rate until blowout occurs, all the while keeping the fuel flow rate fixed. This trajectory through the velocity and equivalence ratio space is shown by the solid black line in the figure to the right. As the airflow rate increases, the reactant velocity increases and the flame becomes leaner. This process is repeated using different fuel flows to identify different positions on the blowout curve. The measured position of the blowout curve is weakly dependent on the trajectory taken through the velocity equivalence ratio space, both the path and the speed. This is due to thermal inertia and the probabilistic nature of turbulent fluctuations that trigger the blowout events. The thermal inertia is small on this rig because the bluff body is the only part of the rig that heats up significantly. The dashed lines shown on the figure show alternative trajectories. The advantages of the trajectory we use here is that only one mass flow is changing, so there is less uncertainty due to overshoots and delays in the mass flow controller response, and also that the path happens to be relatively perpendicular to the blowout curve for the part of the curve we are measuring, which reduces scatter in the data. OH PLIF images of the blowout events were acquired at 10 kHz using an intensified camera and a bandpass filter centered at 310 nanometers with a 10 nanometer width. This figure shows the measured blowout curves. Throughout the talk, blue markers or lines are used for the ammonia blend. Black markers or lines are used for the methane. If you consider the equivalence ratio range where we achieved blow-off for both fuels, the shaded gray range on the figure, blowout occurs for the ammonia blend at a port velocity that is an order of magnitude higher than for methane. Remember that many of the laminar flame properties are almost identical for the same equivalence ratio. Blowout of the ammonia blend at an equivalence ratio greater than 0.65 required reactant velocities exceeding 140 meters per second, and that exceeded the limits of our mass flow controls. The extreme resistance to blowout was a surprise to us because, as we'll show, blowout correlations predict a much smaller difference. Blowout is generally considered to occur at a critical Damkohler number, which is the ratio of a flow timescale and a chemical timescale. We'll first consider a simple blowout correlation and later address more complex correlations. In the simplest correlations, The critical Damkohler number is a constant for a given stabilization geometry, so independent of Reynolds number, Lewis number, or anything else. And the flow time scale is typically considered to be inversely proportional to the bulk velocity. These two assumptions imply that if you consider any two blowout events, the ratio of blowout velocities should be equal to the inverse of the ratio of chemical timescales. Put another way, an order of magnitude difference in the blowout velocity suggests an order of magnitude difference in the chemical timescale. There is no real consensus regarding the appropriate chemical timescale in these correlations. To see whether our results were consistent with existing correlations, we considered 3 chemical timescales computed using Cantera simulations: the premixed flame time, which is a measure of the time that a fluid particle spends within the flame, the blowout residence time of a perfectly stirred reactor, and the inverse of the extinction strain rate. In the next 2 slides, we'll show that none of these chemical timescales account for the observed differences in blowout velocity. Consider blowout points that occur at an equivalence ratio of 0.6 for both fuels. The point on the methane flame blowout curve is labeled M1. The point on the ammonia blend curve is labeled A1. These flames have very similar laminar flame properties, listed in the table on the top right here. That's adiabatic flame temperature, unstretched laminar flame speed, and thermal flame thickness. But you'll notice an order of magnitude difference in the blowout velocity. The videos on the right show OH-PLIF image sequences of the blowout event. Because both are imaged at 10 kHz, the methane flame is well time resolved, whereas the ammonia blend flame is not. However, in both, you can see that there is flame on the shear layers. It repeatedly extinguishes and re-establishes there. And there is also flame near the center axis when pockets of reactants are pulled in from the downstream end of the recirculation zone. As mentioned on the previous slide, an order of magnitude difference in the blowout velocity suggests an order of magnitude difference in the chemical timescale. However, if you look at the table here, none of the chemical timescales we considered have a difference of that magnitude, chemical timescales down here. The ratio of the chemical timescales is given in the table with the red border. This result doesn't necessarily mean that we're considering the wrong chemical timescale. There are more complex correlations we could consider. For example, it has been proposed that both the flow timescale and critical Damkohler number are functions of Reynolds number. To demonstrate that this cannot account for our results, we can consider blowout points that occur at the same blowout velocity instead of at the same equivalence ratio. Consider the blowout points at 40 meters per second, labeled M2 and A2. The flow timescale is identical, and so the chemical timescale should also be identical. However, all the chemical timescales are much lower for the methane flame. This suggests the methane flame, case M2, should blow out at a much higher bulk velocity than the ammonia blend flame, case A2. The ratio closest to unity is given by the extinction strain rates at 0.17. This suggests to us that existing Damkohler criteria may be missing some crucial physics. The obvious difference between the fuels is the Lewis number. Hydrogen flames are known to respond to turbulence very differently from methane flames, and the extinction strain rate of laminar flames is perhaps an insufficient measure of these differences. This motivated us to do DNS, to look at the flame turbulence interactions for these two fuels. And the rest of the presentation will present that work. We ran 2 DNS, one for the ammonia blend premixed with air and one for methane and air, in a temporal jet configuration that features strong shear-driven turbulence. A cross-section of the 3D numerical domain is shown on the left. There is a jet with width denoted by H subscript J traveling from left to right in the center of the domain. Planar flames are initiated some distance away from the shear layer so that they reach the shear layer after approximately 10 jet times, where 1 jet time is the ratio of the jet width and velocity. In both simulations, the domains are the same size and the jet has the same velocity of 115 meters per second. To make the simulations numerically tractable, we used reduced mechanisms, a 19-species mechanism for the ammonia blend and a 16-species mechanism for the methane flame. Details of those mechanisms can be found in the references at the bottom of the slide. A preheat temperature of 750 Kelvin is used and the equivalence ratio is 0.45. The figure on the right shows the regime diagram. The points are computed at the location of maximum turbulence Reynolds number, and the evolution in time is shown by the color. The flames are close to the border of the broken reaction zone regime and the thin reaction zone regime. This figure is just for the ammonia blend, but the methane simulation is similar. This video shows OH mass fractions on an XY plane from both simulations. Interaction with the turbulence starts at about 10 jet times. It's clear that the ammonia blend shows faster flame surface generation and more wrinkling. We also see that the OH layers are less disrupted in the ammonia flame, indicating stronger burning overall. You'll see this more clearly in the heat release rate plots on the next slide. The plot at the top left shows the heat release rate in an XY plane for the ammonia blend simulation after 21 jet times. Values are normalized by the maximum values in the unstrained laminar flame. To the right of that plot is the same heat release rate plot for the methane flame simulation. Notice the difference in scales here and here. There are regions of strongly enhanced burning in the ammonia blend flame that we don't see in the methane flame. Below the heat release rate plots are plots of the OH mass fraction at the same instant. The plot at top right shows the fuel consumption speed and the flame surface density versus normalized time. Both increase more strongly for the ammonia blend flame. The plot at bottom right shows the stretch factor, I subscript 0. It stays close to 1 for the methane flame, but almost doubles for the ammonia blend flame. To understand this, we'll now look at the average flame structure. The two plots on the left are joint PDFs of heat release rate and progress variable, using a progress variable based on the water mass fraction. The black lines showed the laminar unstrained solutions, and the red lines showed laminar strained solutions close to extinction. In the ammonia blend, there is a significant amplification of the heat release rate over the whole progress variable range, and also shows a considerable amount of heat release at low progress variables that is not observed for the laminar unstrained flame. That is, the samples are almost all above the black curve down here. The methane flame, on the other hand, shows a significant number of samples with heat release rates lower than the unstrained laminar flame solution, that is, below the black curve. Here. The plot on the right shows the conditional mean of heat release rate versus the progress variable, again compared to the laminar unstrained flame solutions shown by the dashed lines. The difference for the ammonia blend is very large. You can see that here. But for the turbulent methane flame, it is on average almost the same as the unstrained laminar flame. A major contributor to the differences shown in the last few slides is the high diffusivity of hydrogen. The plots on this slide are all from the ammonia blend simulation and show the effects of preferential diffusion. The leftmost plot shows the atomic hydrogen to nitrogen ratio, and next to it is a plot of the OH mass fraction at the same instant. There are regions with high hydrogen to nitrogen ratio that coincide with high OH mass fractions. For example, here and here. These regions are superadiabatic through local enrichment of hydrogen and are characteristic of flames with Lewis numbers less than 1. The right two plots show the mean local equivalence ratio and the local heat release rate, conditioned on curvature and progress variable. Superadiabatic regions are seen for positive curvatures and are due to the focusing of fuel H2, so that's up here, the positive curvatures. These plots show the overall effect of the thermodiffusive instability is enhanced burning, which leads to higher resistance to strain. So to summarize, we conducted a joint experimental and numerical study of the blowout behavior of ammonia, hydrogen, nitrogen air flames, blended to match laminar flame properties of lean methane air flames. In experiments, unconfined blowout occurred for the ammonia blend at a velocity an order of magnitude higher than for methane flames. DNS of a slot jet configuration revealed that the ammonia blend exhibits strongly enhanced heat release rates and suggests that high hydrogen diffusivity is playing an important role even in highly turbulent flames. And future work will focus on further understanding the role of hydrogen diffusion in turbulent flames and the effects of pressure and the generation of nitrogen oxides. And before we end, we would like to again acknowledge our partners and sponsors. Thank you.